Pluto, the confounding bantam planet. Pluto, the cryptic bantam planet living at the external spans of our nearby planet group, is working up further inside the galactic local area. Ongoing reports indicate a potential encounter with Neptune, raising worries among researchers and space lovers alike. Famous specialists, including Neil deGrasse Tyson and Michio Kaku, have sounded alarms about the possible outcomes of this divine conflict. Yet, how did Pluto end up on an impact course with its far-off neighbor, and what could this astronomical crash mean for us here on Earth? Let's investigate this unfolding event. Once considered an undeniable planet, Pluto was subsequently renamed as a bantam planet because of its extreme orbit. Regardless of this transformation, it continues to spellbind and attract stargazers. Recent predictions from prominent researchers highlight a troubling proximity between Pluto's path and that of Neptune. These specialists warn against a potential crash between the two planets, representing a critical danger to Earth. Pluto's journey around the Sun is marked by its unique characteristics within our nearby planet group. Its orbit spans an enormous 248 years, and since its discovery in 1930, Pluto has yet to complete a full revolution. Adding to its intrigue is the highly elliptical shape of its orbit, a deviation from the nearly round orbits of the major planets. Additionally, Pluto's orbit is inclined at 17 degrees to the ecliptic plane, making its path steeper compared to other planets. One notable aspect of Pluto's orbit is its intersection with Neptune's path. For approximately 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, defying expectations based on their respective positions in the solar system. So why hasn't a crash occurred between Pluto and Neptune? The explanation lies in the gravitational effects exerted by other planets. The study of Pluto's orbit began shortly after its discovery, presenting a puzzling challenge for astronomers. Unlike most planets, whose orbits align relatively close to the ecliptic plane, Pluto's distinct features include a steep inclination and an elliptical shape. The mystery deepened with the realization that Pluto's orbit crosses Neptune's. The stability of Pluto's orbit amidst these complexities serves as evidence of the intricacies inherent in celestial mechanics. The three-body problem in space involves understanding the movement and gravitational interactions among three celestial bodies, such as Pluto, Neptune, and the Sun. This problem explains the complex interplay of their orbits and gravitational forces. Terms like libration, semi-major axis, and the KAI mechanism contribute to unraveling this celestial enigma. Astrophysicists state that the libration mechanism responsible for maintaining planets in their orbits plays a crucial role concerning Pluto and Neptune. This term suggests that when Pluto crosses Neptune's orbit, it is positioned no less than 90 degrees away from Neptune, effectively preventing potential collisions. The KAI mechanism ensures that when Pluto approaches Neptune or other giant planets, it is positioned entirely above their orbital plane, providing an extra layer of protection against impacts. The KAI mechanism explains why Pluto's orbit around the Sun appears erratic but remains stable over the long term. Despite apparent randomness, space simulations in the late 1980s revealed that, despite stable properties, Pluto's orbit is actually chaotic, with minor initial deviations leading to significant changes over thousands of years. Nevertheless, Pluto's unusual orbit maintains stability over incredibly long timescales, keeping disorder under control. Recent computer models have improved our understanding of how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune's unique relationship with Pluto, completing 3 orbits for every 2 of Pluto's, significantly contributes to the stability of Pluto's orbit. Additionally, Jupiter's immense gravity exerts a major influence, while Saturn's effect, though smaller, also plays a role. Through detailed studies, scientists have shown that the combined effects of Neptune, Jupiter, and Saturn ensure the safe and stable movement of Pluto in space for billions of years. These phenomena are crucial for maintaining the order and consistency of celestial movements in the universe. Without these mechanisms, the solar system would be prone to greater turmoil and instability, potentially leading to collisions or ejections from stable paths and causing cascading effects on other celestial bodies. Understanding Pluto's orbit is especially important in discussions about a potential future collision with Neptune. This data provides a clearer understanding of the dynamic nature of the planetary system. Pluto's case highlights how seemingly unstable orbits can achieve stability through the complex interplay of gravitational forces and orbital mechanics. Ongoing observation and analysis of these phenomena are essential for gaining a better grasp of our place in the universe. Exploring the depths of space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit serves as a fascinating example of this unpredictability. The concept of orbital chaos strikingly illustrates the delicate dependence of a celestial body's path on its initial conditions. For Pluto, even slight variations in the dwarf planet's position or velocity can significantly alter its long-term orbit. Computer simulations have been instrumental in helping researchers understand how Pluto moves in space. By making minor adjustments in these simulations, astronomers can observe how small changes can have a significant impact on Pluto's trajectory. In the late 1980s, these simulations uncovered an intriguing aspect of Pluto's orbit. Despite features like libration and the KAI mechanism contributing to its stability, Pluto's orbit can still exhibit irregularities. Even a small initial difference in Pluto's position or speed can lead to substantial changes in its orbit over many years. Despite this inherent chaos, Pluto's orbit remains stable for an astonishingly long time, extending over billions of years. This suggests that beneath its seemingly erratic appearance, Pluto's journey around the Sun follows a structured order. Anticipating cosmic events and predicting the future paths of celestial bodies, especially those with eccentric orbits like Pluto, is challenging. The inherent volatility of these systems makes long-term predictions uncertain. Computer models help us understand and anticipate the future paths of celestial bodies, but they also reveal the limitations of our predictive capabilities. These models heavily rely on accurate initial conditions and replicate complex interactions. Even a small error can lead to significantly different outcomes, making precise predictions difficult. The tumultuous nature of celestial orbits, such as Pluto's, reminds us of the ever-changing universe. While we have made progress in understanding space, Pluto's case highlights our ongoing limited knowledge. Understanding the gravitational effects of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how each planet's presence and position can influence the stability and trajectory of other bodies in the system. Despite these complex forces, prominent astrophysicists are expressing concerns about a potential collision between Pluto and Neptune. Neil deGrasse Tyson, a renowned astrophysicist known for renaming Pluto as a dwarf planet rather than a major planet, offers a unique perspective on the mysteries of our solar system, particularly regarding Pluto. Tyson, known for his insightful views on cosmic mechanics, sees Pluto's renaming not as a downgrade, but as a necessary adjustment to our evolving understanding of the celestial objects surrounding the Sun. His approach to celestial mechanics involves continuous learning and adaptation. He views the complexities of orbits like Pluto's as a sign of how much more there is to discover in space. Tyson believes that the allure of these questions makes cosmology so fascinating. Moreover, Tyson is aware of how space-related events and discoveries capture public interest in astronomy. He believes events like Pluto's renaming and its unusual orbit are valuable opportunities to engage the public's imagination and curiosity about the universe. By discussing the dynamic and sometimes peculiar aspects of cosmic mechanics, Tyson aims to foster a deeper understanding and enthusiasm for the universe. He opens a window for the general public to marvel at the wonders and mysteries of the universe. Working alongside other researchers, Tyson actively warns the public about the potential risk of Pluto's erratic path. After extensive review of Pluto, he has raised concerns that the three-body problem could pose a serious threat, suggesting that a collision with Neptune may be overdue. Furthermore, Tyson emphasizes how such a collision could disrupt the balance of the universe and lead to catastrophic consequences extending to Earth. A collision between Pluto and Neptune would be a rare and catastrophic event in our solar system. This impact would release an enormous amount of energy, potentially shattering Pluto due to its smaller size and icy composition. Debris from the collision could disperse across the solar system, posing potential risks to other planets and their moons. For Neptune, such an impact could potentially alter its atmosphere and orbit, depending on the specific details of the collision. Michio Kaku, a prominent theoretical physicist known for his work in string theory and science popularization, offers a novel perspective on this scenario. His views on the future of space exploration and the relationship between celestial mechanics and theoretical physics provide deep insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital characteristics of celestial bodies like Pluto, according to Kaku, can offer essential insights for future space missions. This knowledge can assist in navigating the solar system more effectively, predicting potential hazards, and planning missions to the outer reaches of our solar system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to explore other celestial bodies, providing a roadmap for approaching and understanding distant worlds. While discussing the physics of planets, Kaku frequently highlights the profound connection between celestial mechanics and theoretical physics. He believes that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated events but are linked to fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, aims to understand these principles at the most fundamental level. He suggests that examining the complexities of celestial mechanics, like Pluto's orbit, can yield insights into the underlying laws of the universe. Like Tyson, Kaku has also addressed the potential collision, relating it to his theories about the universe. If Pluto and Neptune were to collide, it would be a significant event in astronomy, offering an extraordinary observational opportunity that could potentially contribute to our understanding of string theory. String theory, a theoretical framework that replaces point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. The impact of such magnitude in the solar system could create extreme conditions of energy and gravity, offering insights into the behavior of fundamental particles and forces under extreme circumstances. A key focus in string theory. The gravitational waves generated by the collision could provide valuable data for testing predictions related to string theory, gravity, and spacetime. While the direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be significant, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit serves as a unique example of celestial mechanics, demonstrating both stability and chaos within our solar system. The distinctive attributes of its orbit, influenced by the gravitational forces of neighboring planets, particularly Neptune, highlight the unpredictable and dynamic nature of space. The universe holds many secrets, and the three-body problem is just one of them. There are other potential catastrophes that scientists anticipate. While the likelihood of planets colliding in space is very low, it is not entirely impossible. The way planetary orbits are influenced by various factors, including gravitational interactions, is explained by the three-body problem. In some space systems, like TRAPPIST-1, with 7 Earth-sized planets, gravitational forces create a rhythmic pattern called orbital resonances. Over time, these patterns can make planetary paths less stable, potentially leading to collisions. Despite the crowded nature of systems like TRAPPIST-1, impacts are not currently occurring. Scientists closely monitor these systems to understand how planets affect each other's paths, especially when they are close together. This information helps us appreciate the movement of planets in space. Rogue planets drifting through space without orbiting a star present an additional unusual factor. These planets, once part of a star system, are ejected due to gravitational disturbances or other celestial events, such as the close passage of another star or dynamic instability in their original systems. Over time, these wandering planets can traverse vast distances, potentially reaching areas far from their original location. During their solitary journey, there is a possibility of them intersecting with other star systems. If one of these rogue planets were to enter another planetary system, there is a slight chance of a collision with a planet in that system. However, given the vast and predominantly empty nature of space, the likelihood of a rogue planet directly impacting another planet is extremely low. The vastness of interstellar distances and the scarcity of planets in open space act as deterrents against frequent collisions. Furthermore, Rogue planets are relatively rare compared to the number of stars and planets in stable orbits, making such encounters even less likely.